the next rate that we're going to look at is a specific one, that being growth and decay. Now, we're going to look at two situations. The first one is as far as, say, 2-unit would go with it. They look at a very simplified model, but we'll look at that first, and then we'll look at the 3-unit model, how we expand on that. So growth and decay, it follows a basic idea that growth and decay is proportional to the population. More people you have, the higher the births, the higher the deaths. That's the basic idea. So if we convert that into a differential equation, the P to T, the rate of change of population with time, we've just said it's proportional, so that's the same as saying equal to some constant times the population. So we start with that. Well, it's in terms of P, so I'm going to turn both sides upside down. And I'll get the T to P is 1 on KP. So T is 1 over K, the integral of the P on P. And integrate the P on P, we get log P. Plus, of course, a constant. So multiply both sides by K. Remember, I'm trying to come up with an equation for P. I'm trying to make P the subject here. So log P will be KT minus C. To undo a log, we'll exponentialize. So we get e to the kt minus c, which I'm going to break up by using my index laws. I'm going to say that's e to the kt times e to the minus c. The reason I've done that is e to the power of minus a constant is a constant in itself. So I can simply rewrite it as p equals ae to the kt. Now, the reason I've boxed it is because they've sucked the life out of this particular type of question, right? Because all you have to do now is, you don't have to derive it every single time. You see the equation to P to T equals Kp, you can just jump to, oh, P equals ae to the kt. Thus, what we're looking at is an application of calculus where we don't use calculus. No, spoils all the fun. I can see you're disappointed. Pretty much just becomes a substitution question, to be honest. So the P to T equals Kp. We can just say, oh, well, that means the solution is P equals ae to the kt. P represents the population at any particular time. A would end up being the initial population if you think about it, because if you sub in T equals 0, we'd have e to the power of 0, which is 1. So P would equal A. And K is our growth, or if it was negative, our decay constant. T, of course, represents time. So let's have a look at one. We know the growth rate of population of bacteria, those little bacteria. They're very quick little reproducers, bacteria. 10% of the population, that's the growth rate per hour. The initial is, how many zeros have I got there? 1 million. We've got 1 million of the little gooby wops that are all over your hand at the moment. And you don't see them because they're so small. But they're all there, trust me, covering your hand. Now, the first part here is to say, show that. Now, by show that, you don't have to go through that process I just did. You do it in reverse. Because they've said show that, I've got the final answer. So I can say, well, P is equal to ae to the minus, in this case, 0.1t, because K is 10%. And I'll just differentiate. So to P to T then, differentiate the power, we get 0.1, so it becomes 0.1a e to the 0.1t, which is 0.1 times P. So the P to T is equal to some constant times the population. So indeed, that does satisfy our growth and decay equation. So rather than doing it in reverse and using calculus that way by integrating and finding it all, I suppose we do get to use a little bit of calculus here, but all we've got to do is differentiate an exponential function and show that it works. All right, we're going to work out how many are now covering our head. After 3.5 hours, started off with 1 million of them. I've got to work out the initial population. Well, the initial population we know is 1 million. They've told us that. So our formula becomes 1 million e to the 0.1t. Now, of course, if you did forget that A is simply the initial population, then you'd go, oh, when T equals 0, P equals 1 million. Oh, therefore A is 1 million, because when you substitute it in, you get 1 million. There's our formula. We want to know after 3.5 hours. Well, sub 3.5 into our formula, and we get 1,419,000. It's almost 50% more. That's after 3.5 hours. All right, we're going to look at another example. We're on an island. In 1960, the population was 1,732. So a little remote island. But unfortunately, on this island, the people didn't get on with each other. And in 1970, the population is now 1,260. Yeah, they just sort of had a few fights. Oh, well, there's another one gone. Find the annual growth rates, which will end up being negative, of course, because we can see it's actually going down, assuming it's proportional to population. So, all right, they've told us to P to T is equal to KP. From there, I can say, oh, well, that means P equals AE to the KT. Well, we've got to work out our constants. We know the initial population is 1,732. So we have 1,732 e to the KT, but I still need to work out K. That's what this question is. So when T equals 10, because it's 10 years later, P is 1,260. All right, 1,260 is 1,732 e to the 10K. We want to make K the subject. So e to the 10K is 1,260 on 1,732. So to undo the exponential, I log both sides. 10K is the log of, I mean, that fraction does simplify down. I just haven't bothered. And then we divide by 10. So K is 1/10. And you might be thinking, hang on, you said K was negative. But remember, a log of a number smaller than 1 is a negative number. So that log would actually be negative there. Turns out to be, they wanted it to, they didn't actually say how, to the nearest percent, there it is. It did say to the nearest percent. So that is negative 0.0318165. So to the nearest percent, negative 3%. 3%. So in how many years will the population be halved? So we want to know where the population is 866. Notice I've left K as just K. But obviously I've got that number stored in my calculator that I can use. Or I could use the exact value as well. So e to the KT ends up being a half. Those of you that don't know which subject, physics or chemistry or both, do you do radioactive decay? You recognise that? That's a simple little formula for half-life.
I don't think we got that.
Oh, you don't have to do maths in chem. Heaven forbid there'll be any maths in science. Okay, that is actually a formula for the half-life of anything. And K just is the decay rate. You put the decay rate in and you can work it out. Because that's what we're saying. We're saying when is the population 1/2? So e to the KT would be 1/2. Log both sides and we get our formula. We want to work out T. So when we sub it in, remember that K we've stored into our calculator, 21.786. So after how many years will the population be half? Well, it'll be after 22 years. Now, if the answer had been 21.2, what would the answer be? Still be 22 years. Because after 21 years, it hasn't halved yet. So it's 21.2. But some people get caught up in, should we round off or shouldn't we round off? I always feel if you put your calculator answer down and then justify your answer why you decided to round down or round up, they're not going to take marks off because they can see you know what you're doing. You've worked out the problem. So if you had gone, say, 21.2, but then you said, to the nearest year, that's 21 years or something like that, they're going to give you the mark. All right, so as I say, that's the basic one that Tuna would look at.